Now, some of you may already notice that, wait a minute, this seems to be the same answer for one of the, a little bit lengthy example. Maybe I think that's example 1, right? Is that example 1 or example 2? And so let's summarize this result. This is page 22. And in the summary, we are looking at step 7. You remember we did this. There's one example where we consider a bin column. And it has this force P, and also force Q, remember? Right? We did this example. And what was the critical load? Of course, I know that's from your previous notes. You know from here, critical load is pi squared EI over L squared, right? What about our case? The case we just solved is this. This is what we did. It's also simply supported. P is here, P is here. And this distance is what we call eccentricity, right? So what's the critical load? Still the same. Is that a coincidence? Because this two problem looks completely different, right? Correct? It certainly shouldn't strike you that these two problems look the same. They're different. Subjected to different loading condition, may even have different structure condition. How come the critical loads are the same? Is something fishy going on here? In fact, that's the first lesson in the bucklings of columns. In the buckling of columns, actually, that's the probably also true for the buckling of many other structural systems. What actually affects the buckling is only two important elements. The first one is, what is the magnitude of axial force? Because in the first case, there's no bending moment, right? The case we did before is shown only axial force. But in the case we did it now, if you move this P from this one to, from the up position to the support, you're gonna get this. It actually equals to a force like this, plus a moment, right? So that actually equals to this. When you move the P from the end of this extrusion part to the support, it actually equals to the combined action of an axial force P and the bending moment. And the moment is, as you already know, is just P times E. Correct? So that's what we did. That's how we solved this problem. So you actually move the P here, then you have two things. Maybe we should do that. I just don't want to mess up the whole thing. But it really looks like this. This is P times E. There's also another P here. Right? In the first problem, you have the axial force, no moment. In the second problem, you have axial force and the moment. In the first problem, you have a lateral force, a vertical force, which is this force Q. In the second problem, there's no Q. So what does that tell you? Logically, that tells you that with or without moment at the support doesn't matter. it doesn't change the buckling load. So that's one lesson. 2, with or without the lateral force, with or without the Q, doesn't matter, right? You still will be getting the same critical load. So what really matters? So this is the answer. The 2 things really matters in column bucklings is first, your force, axial force. Only axial force matters. Whether it is a 1P or 2P or 3P, that makes a huge difference. Moments, they don't matter. So the axial force is really the important one. And the other important factor is boundary conditions. What these two structures share, or what these two structures have in common, is their boundary condition. And that means you have to notice that if they have the same boundary condition, and they have the same axial force, you know that even you add other things to the structure, it will not change the buckling load at all. So let's be creative here. If that deduction is true, and what do we have? We have actually lots of possibilities. For example, let's consider this. Consider that I have a column, and the column is subjected to lots of crazy things, but I still have the axial force here. So in addition to having one Q, we can actually put them all together, right? So let's add one more Q here. And maybe we can add another, let's call it Q1. Maybe we can add another one, Q2, right? And also let's move the force from the P to another place. Let's make it to what? To here. Let's consider eccentricity. So your loading force P becomes right here. P is X right here. Now I combine these two. Now please tell me what is the critical load in this case?
The same.
It's still the same. It's still pi square EI over L square. So please understand what this means. Okay, any questions? All right, now let me come back to my slides because there are a few things I have to explain to you. Even though that from this example, everything may look so happy and so perfect, but there are other things we have to be aware of. The first lesson is we enjoy using these general assumptions in the classical column theory. However, in reality, look at how columns buckle. When you look at the actual buckling like this, you know that we did not consider the cross-sectional area. We only use mass moment of inertia I to describe a cross-section, but the cross-section can be very different. The one on the left is a hollow column, right? I'm sorry, the picture on the left is a hollow column, and the one on the right is an I-beam column, which is this one with called B3. There are two different columns. When they buckle, they exhibit totally different modes. And that means whatever we have using here so far, you can only use it to analyze the global buckling, not the local buckling. That's the limitation of the buckling theory that we use so far. However, when we move to the beam column buckling, we can study local buckling. So this classical column theory only applies to global buckling. You can calculate the buckling load, but you don't know how the cross-section is going to buckle. Why? Because you have different kind of cross-section, even so they all share the same value of mass moment of inertia. You certainly know we can do it, right? I can create two different cross-sections. One is a hollow, the other is an I-beam. And they all have the same value of mass moment of inertia. Would you agree? Is it possible? Of course it's possible. But when it comes to buckling, they may give you totally different modes. They will look totally different. Another issue with the column buckling is this. We have not really talked about it because it's not that important or significant for column buckling, but for beam cup buckling, that is extremely crucial. That's what we call the torsional effect, or the effect of torque. For beams, because beam connects to slabs, when slabs deform, they not necessarily will result in a symmetric deflection. That means the slabs can actually tilt. And when the slabs tilt, the underneath the beam will usually just being twisted. When there's an axial force acting on beams, that will result in what we call torsional buckling. In this case, is the torsional buckling mode for columns. That is not that common, but for beams, that's very common. So another issue we have to consider here is when the axial buckling, where the classical theory predict the global buckling, coupled with torsion, and the answer will not be this. The answer will be different. So that's also another limitation you want to pay attention to. So look at the details, and this perhaps applies more to beam buckling, not really for the buckling. You notice the warping on the flange side. Of course, if you use a hollow cross section, this won't happen because you don't have flanges in the hollow cross section. Now, from the steel designs, you have learned the different boundary condition and use what we call the effective length, and that's what we're going to talk about today. How do we calculate this effective length from theory? From steel design, you've been provided with a table, right? And from the table, it tells you that there's an effective length coefficient, the capital K, and by multiply this, you can just calculate it. But you need to know why these values sometimes is 0.5, sometimes it's 0.7, sometimes it's 0.85. That's what we want to cover here. And certainly, global buckling theory cannot predict the deformation of detail, like in this case, detail components such as reinforcement. Numerical simulations can give you some ideas about how we can predict the buckling, but it will not tell you what is the buckling load. This has to be separately calculated. But what the numerical simulation can do is to tell you where will be the location that buckling likely to occur. Now the difference between this in these two different cases is the simulation on the right does not have diaphragms, and the simulation on the right, that case, it has different diaphragms. Mechanically speaking, the one on the left indicates a higher buckling mode, and the one on the right shows the lower buckling mode. So we already talked about this one. Now let's come back to get this expression. What is amplification factor AF? That is actually the continuation of this example. So we're going to continue with step 8. And from the previous case, we already know that Y maximum, because Y maximum, which is this example, we already found that Y maximum equals to second K over 2 minus 1 times eccentricity E, right? That's what we found in step 6. We found that. Now, if I want to write it, I want to write like this. I want to write that if we let this what we call delta maxima to be Y maxima plus E, that means this means what? That means I want to separate the eccentricity effect by writing it this way. Okay, and that means what? I mean, this is a total deflection.